Good morning. I would like to welcome you to the 150th anniversary virtual Festival of Art, Science and Ideas at Newnham College. My name is Roisin Owens. I'm a professor of bioelectronics at the Department of Chemical Engineering and Biotechnology here in Cambridge. I'm also a fellow at Newnham College and deputy admissions tutor for STEM subjects. I'm delighted to be able to introduce this lecture this morning. So we'll have Professor Carolyn Crawford, who's an alumna of Newnham College. For those of you who are thinking about A-level subjects in the context of today's talk, she did A-levels in maths, further maths and physics, and then went on to read maths at Newnham College in Cambridge. She did a PhD in astronomy, studying at the Institute of Astronomy, and she studied the immediate environments of both the most massive galaxies, those found at the centers of clusters of galaxies, and those relatively nearby by today's standards. Her career highlights include being public astronomer at the Institute of Astronomy, professor of astronomy at Gresham College, and fellow and tutor of Emmanuel College. Although she's now retired, Carolyn still enjoys communicating the excitement of astronomy to as wide an audience as possible, and she makes regular appearances on radio programs such as In Our Times. Her outstanding abilities at science communication were recognised in 2009 by a Women of Outstanding Achievement Award by the UK Resource Centre for Women in Science, Engineering and Technology. Today, she'll be giving us an introduction to the Milky Way, and we're all very much looking forward to hearing this talk. If you have questions during the talk, what you can do is type them into the questions and answers box. And then at the end of the talk, I will be asking some of your questions to Carolyn, depending on how much time we have. Carolyn has also very kindly agreed to answer some additional questions by email later on, and we'll give you the details for her email address. So without further ado, over to you, Carolyn. We're very much looking forward to hearing you speak.
Thank you very much for that introduction, Roisin. Okay, so today I'm talking about our home. And this is our home, not in the sense of our planet or even our solar system, but putting them both in the context of the wider galaxy that we live in, the Milky Way. And this is something that contains so many things. We're going to be talking about black holes, going to be talking about the interstellar medium, full of clouds of gas and dust, planets around other stars and the other kind of stars that are out there. But first, let's just see about what you might know, you might have seen of the Milky Way itself. If you're lucky enough and you have a really dark night, and I will confess it helps if you're in the southern hemisphere because that's where the center of the galaxy is, you can see the Milky Way as just a broad, diffuse band of light overhead. And it depends where you are, as I say, on the Earth, and it depends on the time of year, and you really need a good dark moonless night. And when ancient astronomers and ancient people saw the Milky Way, they didn't know what it was. I mean, first they thought it was something in the atmosphere. And of course, the name, the Milky Way, comes from the idea that it's the breast milk of Juno that was sort of spilt across the sky when feeding her infant. And it wasn't until much later on, so you get to more sort of the Middle Ages, when it was shown that it must lie somewhere beyond the moon, not be in the atmosphere and Earth. And it wasn't until he got to Galileo, who first turned a telescope onto the skies, and he looked at the Milky Way, and he saw that it wasn't just this diffuse light, that in fact it was made up of thousands and thousands of stars. And the fact they all appear tiny meant they are at immense distances. So when you see the Milky Way in the sky, it is just that band of stars that is our home galaxy. If we could go outside our galaxy, which I want to stress we can't, and I have some of this, you're going to have to go on an imagination trip with me. We've barely left our own solar system. We certainly can't leave our own solar system and fly outside our galaxy. But if we could, and we could look down on it, we think it would look something like this. It's a large spiral system. And if you want to know, as I say, the context of the solar system, the short answer is you are here, about halfway from the center to the edge of the galaxy in one of these luminous spiral arms that you see. And our sun is just one of around 100,000 million stars that make up our galaxy. And we're all rotating around the center. You may think that you're sitting pretty still in front of your computer on a Sunday morning, but in fact, you are on a planet that is going at 30 kilometers per second around the sun, that is actually rotating round the center of the galaxy at 220 kilometers per second. So a phenomenal speed. And even at that speed, it still takes us 240 million years to go once round our galaxy. And the whole structure is huge. It's 100,000 light years across. And a light year is the distance that light travels in 1 year. So that's 9.5 million kilometers. So this is an example of the huge numbers and scales and sizes that we talk about within astronomy. This, of course, is our galaxy if we saw it face on. When we look at other galaxies out there in space that we think resemble our own Milky Way, sometimes we see them like this, but sometimes we see them edge on. And you'll find that the shape of the galaxy is much more like, almost like two fried eggs stuck back to back. And we live in the flat disk, if you like, the egg white of the galaxy, again, about halfway from the center to the edge. And if you think about that, when we look at our own galaxy, we see it edge on, much like we do this external galaxy. So compare this to our own view of the Milky Way in the night sky. And you can see why it appears as a comparatively thin band of stars stretching across, because we are seeing it with that edge-on view. Now, almost every star, every star basically you see in the night sky is a member of our galaxy. And they are all these stars are suns just like our own, in the sense that they're a sun, but they are wildly differing. You can just see in this image, you've got blue stars, you've got red stars, you've got massive stars. They're at different temperatures, they're different sizes, they're different colors. There's a huge variety out there. And to give you a sense, again, of putting a context of our solar system in our own sun in context of the other stars out there, here's a little movie where we start off with something very familiar, which is the moon, and showing to scale the planet Mercury and then the planet Mars. And then you have Venus, which is about the same size as the Earth. Now watch the huge jump to see before you get to the smallest of the gas giants, which is Neptune, and then to Saturn. And you could fit 1,000 Earths inside Jupiter, but you would need 1,000 Jupiters to fit inside our sun. And our sun is a very average star. It's called a dwarf star. It's very mediocre. It's not the smallest, it's not the largest. But here we're scanning through some of the large stars that we can see with the unaided eye in the night sky. And these are all giant stars. You've got blue giants, which are massive young stars. You've got red giants, which are cool old stars. And what we're doing here is we're working out to the largest known star. And you'll see how it just dwarfs our sun in comparison. So the next star is VY Canis Majoris, which is the largest star where we can measure the size. The size is 2.8 billion kilometers across. That's 2,000 times wider than our sun. And just to show you the Earth in comparison, well, you probably can't even see that on your screen. It's minute. So if we were to fly on a jet plane around the surface of that star, which I wouldn't advise because it's probably quite hot, but imagine we could skirt the surface of that star flying at 900 kilometers an hour, it would still take us 1,100 years to go once around that star. So there's a huge variety of stars within our galaxy. And again, another galaxy from ours, looking down in it, you see very clearly the spiral arms. And what I hope you notice in this, and it's also true of all the previous galaxies I might have shown you, is the center of the galaxy where that bulge is, if you like the egg yolk, it's very white, yellow, red stars. They're older stars, but the spiral arms are lined and traced by blue stars. And these are massive stars. And the way things are, if you see a blue star, it tends to be massive because it's hotter. If you see a red star, it's cooler and it's dimmer and that's older. And to put it in very simplistic terms, a star wants to collapse under gravity. And the only thing that's stopping it is the nuclear fusion at its core. So if you have a very massive star, it's got a lot more gravity, so it has to burn hotter at the center to withstand that gravitational pull. And if something is hotter, it is bluer. So bluer stars are more massive stars. And despite the fact they're more massive, they're having to generate energy at such a rate to counter the gravity that they go through their fuel a lot faster, so they don't live long. And, again, this is astronomy. By long, I mean they only live tens of millions of years, okay, instead of tens of billions of years, which the yellow and the red stars do, and stars like our sun. So if you see a blue star, you know it is hot. You therefore know it is massive, and therefore you know that it's actually relatively recently formed. So this, even just looking at the colors of a spiral galaxy, is telling you immediately that star formation occurs in the spiral arms. And you can see within the spiral arms these clusters of blue stars. If any of you are amateur astronomers, you can see these easily through binoculars or small telescopes. The Pleiades, the Seven Sisters, is one example. And so these stars, the blue star clusters, show you where some of the most recent star formation has occurred. But of course, a galaxy isn't comprised just of the stars and all the different kinds of stars. In between those stars, and invisible mostly to the unaided eye, is the reservoir from which the stars form. It's the interstellar medium, and this is neutral, mostly hydrogen gas that is invisible to our unaided eye. We can see it with radio telescopes, and it's a very sort of diffuse gas that fills the space between the stars. And it's fairly cold and, not obvious until it's in the vicinity of stars. So imagine we've got these stars that you see in the screen here. In between them, there is very cold, neutral hydrogen gas, and some patches of that are colder. And where it's colder, it's denser, and the coldest, densest regions is where stuff is going to be closer together. It's more likely to collapse under gravity, form the stars. And when you form a star, it will pump out energy into that surrounding gas. And if you throw energy at mostly hydrogen gas, you'll excite the atoms and you'll cause it to glow a very characteristic pink color. And so around these newborn stars, you will see what are known as nebulae. And nebula, of course, means a cloud in Latin. So you see clouds in space. So these are just the visible pockets of those large interstellar medium clouds that are being heated to temperatures of thousands of degrees, where the hydrogen will glow this very pink color. So right in the center of this nebula, this is about 100 light years from one side to the other, you will see a cluster of relatively newborn stars. So maybe they're about 4 million years old. And the winds and the energy and the light from those stars have actually blown a cavity or a bubble around them. And then that energy is going out and exciting all the hydrogen gas and creating this beautiful structure. And out beyond there, there's more gas, but it is diffuse and it's cooler and it fades away out of the optical and into the radio wave band. And these nebulae, wherever there are star clusters, they litter the spiral arms of our galaxy. If you ever look at Hubble pictures of nebulae, you will always find a star cluster in the center. So one of the most famous ones, well, okay, here's just, again, a side-on view of our galaxy. And you can see not just the concentration of the stars, but the pink clouds, which are the nebulae. And that's showing you where star formation is occurring. And that gas is not just gas, it's mixed up with something called dust. And by dust, I mean physical particles of, if you like, soot and sand, silicate and carbonate mostly, and they're tiny. Each maybe is about the width of 1,000th the width of a human hair. They're like the minuscule particles you might get in cigarette smoke, very, very tiny particles. But if you get a cloud mixed in with a gas, and it could be light years across, it can still be opaque. So here, when you look at the galaxy, you see the stars, you see the nebulae, but there are also these dark patches. And these are dark not because there aren't stars there, but because there's dust mixed in with the gas and it's opaque. And sometimes, I mean, here's one just towards the center of the galaxy. It's upside down, but it's called the Pipe Nebula. You can probably see why. You can see right in the center, it's actually black. It's obscured all the light from the background stars. So whenever we look at these nebulae, here's another example. You can see the stars in the middle, you can see the gas and the dust, it's lighting up just a cocoon around it. But you have these cold silhouettes of giant dust clouds. And in the center of these, you're not just blocking the light of the stars, you're blocking the heat from the stars. And they drop down to temperatures of just a few tens of degrees above absolute zero. And these tend to be the coldest, the densest regions of the interstellar medium. And within these, you can even have molecules forming, and we can detect molecules, not just ordinary ones like carbon monoxide and water and methane, but predominantly some very complex carbon-based organic compounds within these molecular clouds. Now, because these are the densest regions of our interstellar medium, these are where star formation occurs. And to see where star formation is occurring, I'm going to show you one of the iconic nebulae, certainly that the Hubble Space Telescope has studied. This is called the Eagle Nebula. And you may not recognize it as such, but again, you've got the star cluster, you've got like a cavity where it's illuminating the walls of that cavity and causing the gas. And it's just a different color scheme, which is why this one's portrayed as blue. But if I zoom in right to the center here, you may recognize these pillars. And here you're seeing where the dust is mixed in with the gas to, block out the background light. You can see these pillars are pointing towards the hot stars. And we have a process of erosion. If we look, say, just at the top region of that pillar, and again, to give you a scale, these pillars are about 10 light years long. I hope you can see there is gas just sort of boiling off and eroding from the surface. And it leaves behind the denser regions, these little cocoons. And so you have the edge of a cloud where right at the center here, you might have a slightly denser bit of gas and dust, and the starlight eats into the cloud, then leaves these little sort of tadpole structures. And it's within these that new stars will form. And you can see in regions of this nebula where the lighter, fluffier stuff has been completely eroded away, leaving behind these small, dense cocoons, each, a few times wider than the solar system. And within these cocoons, young stars are forming. So a star forms under gravity, where you have cold, dense regions collapse under gravity. The whole process takes a while. And after you've formed the star at the center and it's switched on, you haven't used everything up in that cocoon. There's enough matter that it settles in a disk around the star because it's rotating, and that is cold and it contains the dust. And that is what we call a protoplanetary disk. Here's an artist's impression. Okay, these are just artist's impression on this page of you get this thick disk, and that goes on in the future to form planetary systems. This is the artist's impression. These are real ones. These are edge-on disks of the very early stages of planetary formation, and they're just backlit against one of these nebulae. And here again are some of those tadpoles in another nebula, and deep within them, perhaps you can see the dusty disks around each star, and those go on to form planets around the stars. So now we study not just stars, but planets around those stars. And it's probably true that in terms of the sky, most stars that we study that are similar to the sun, or perhaps cooler, some of those cooler, redder, more kind of dwarf-like stars. So the ones that are, a few billions of years old, they are all likely to have a star around them, a planet around them. And we call these exoplanets, planets in other solar systems than our own. And the tally as of Friday in terms of discovered planets around other stars, over 4,700, contained in over 3,500 planetary systems. And so that means you've got multiple planetary systems, some with 7, 8 planets around a star. And the interesting thing is these solar systems don't necessarily resemble what we have in our own solar system. And in particular, we're very good at finding planets that are nothing like anything we've got in our own solar system. Some of the easiest planets we've found are things like called hot Jupiters. So these can be things about the size, the mass of Jupiter, but they're orbiting very close to their star, their host star, maybe going around in a matter of days instead of the 11 years or whatever it takes Jupiter and Saturn and the gas giants to go around us. So these are giant planets which are hot and probably gassy planets. And that really throws our understanding of how a solar system forms on its head. And yet one of the most common kinds of planets we see out there is one we don't have in our solar system as well. And it varies. It can sometimes be called a mini Neptune if we think it's gaseous, or even a super Earth. And these are things that bridge that gap in our own solar system between the Earth, the largest of the rocky planets, and Neptune, the smallest of the gas giants. And these are things which, say, like a super Earth could be 10 times the mass of Earth, but only about twice the size and perhaps rocky. And if they're a bit larger, maybe a bit more like the ice giants, we call them mini Neptune. And of course, there are planetary systems. There are also weird systems, again, artist's impression, where you have planetary systems in orbit around two stars in orbit around each other. So there's a whole plethora of different conditions for planets and potentially for life out there within our galaxy. We're characterizing these planets, or even now with our telescopes, characterizing their atmospheres. Imagine you have a star, a planet that passes in front of its star in its orbit. If you observe that passage and the light of the planet as it crosses the star, you get not just the starlight, but the starlight that has been filtered through that atmosphere of the planet and affected by the molecules in the atmosphere. So we can test what the atmosphere is made of. And here's just a schematic for one that's been studied, where it's got not just water in the atmosphere, but titanium oxide, which is a major ingredient of sun cream. So here you have a planet with a sun cream, if you like, in its atmosphere and in its clouds. So there's huge variation of habitats out there. So when you look at our galaxy, you not only see the dust and the blue star clusters and the nebulae, you also have to imagine the planets around those stars. And then, of course, as I said, stars don't live forever. They're not just forming around us, they're dying around us. A star like a sun at the end of its life will puff off its outer layers to form what's called a planetary nebula. Here, it's nothing to do with planets, it's just because it's disc-shaped. So maybe in another 4 billion years, our sun will puff up its outer layers and the center shrinks down to form a white dwarf here at the core. And so we see examples of what we think will happen to our sun in the future. And then if you have a much more massive star, so maybe about 10 times the mass of our sun, it'll end its life sooner in a much more violent explosion that we call a supernova, where the star explodes, a very complicated process where the outer layers are thrown off to form an expanding gas cloud at about 1,000 kilometers per second, well, 500,000 kilometers an hour. You know, here to the left is a real supernova remnant. So this is the remains of an exploded star. It exploded about 1,000 years ago, but the gas clouds are still expanding at over 1,000 kilometers per second. And at the center here, you have the core of the star that's shrunken down under gravity because it's no longer producing that nuclear energy at its core. And it shrinks down until you're squashing the electrons and the protons to make it up the core of the star completely from neutrons. Neutrons don't like being squished. They resist it. So you have a pressure that holds the star at that point against gravity. Unless, of course, it's a much more massive star. As soon as you start getting about 15 or more times the mass of our sun, it goes supernova. The outer layers of the star are again blown off, but the center collapses down to form a black hole. So even squishing neutrons together can't resist the inward pull of gravity. So again, you not just have the dust, the gas, the interstellar medium, the stars, the planets. Our spiral arms are littered with these dead remnants of stars, the neutron stars, the white dwarfs, and the black holes. Of course, the center of our galaxy is hiding something even more spectacular. So if we look towards the bulge of our galaxy here at the side on view. Now we're going to zoom in now, and because we're looking through the dust, first we'll use optical telescopes, but as the zoom carries on, we're going to move to infrared telescopes, which allow us to see through the dust. And right at the core of our galaxy, there is a group of about 30 or so stars right at the core, and astronomers have been studying those for over 20 years. And what we find is these are moving. So here, just showing you the orbits of these stars over a long period. And that, the one with the yellow orbit there has already, had like a 16-year orbit. And the thing is that these are all orbiting a mass that we can't see. Now, from the motions of the stars, we can work out the gravity that they're responding to, and therefore we can weigh the object that they're in orbit around. And we find it's something that's got the mass of 4 million times the mass of the sun. Now, that's not a problem. You can get 4 million times the mass of the sun if you have 4 million stars. However, the volume that these stars are in orbit around is just slightly bigger than our solar system. And as soon as you pack that much mass down into that tiny, tiny little volume, you've got a supermassive black hole. So this is some of the primary evidence for a supermassive black hole at the center of our galaxy. The people who did this study with the stars are recent recipients of the Nobel Prize for Physics. It's amazing stuff. Luckily for us, this is not an accreting black hole. It's gobbled everything in its vicinity, but we know it's there from the motions and the way its gravity is pulling these stars around the core. Now, this idea of using the motions of things to weigh stuff can be continued to weighing our whole galaxy. Remember, I told you the whole galaxy is in rotation around the center. Well, that gives us a way to weigh the galaxy. So if we had our sun out there in space, minding its own business, going along a certain direction, the fact that it's part of a galaxy means that it has an inward gravitational tug towards the center. And that's what deflects the star to go in an orbit around the center. So if you measure the rate at which all the stars are going around the center of our galaxy, and I think this is the only graph I'm showing, but if you had all the mass of the galaxy in the center, so like if you look on the right-hand side, this is what you see for the sun. The sun holds 99.9% of the mass of our solar system, so Mercury moves much faster around the sun than, say, do Neptune and Pluto. The further you go out, the slower things go. That's what you might expect if you plotted the speed of stars around the center here against the distance from the center of the galaxy. That is what you might expect from looking at the way most of the light of the galaxy is in the center. But instead, what we see is that the stars are going too fast, especially in the outskirts of the galaxy. They're whizzing around at such speed, they should have been flung off into space. They shouldn't be held by what we expect to be the gravity of the galaxy. Even the sun is traveling about 75 kilometers per second too fast. And even if you add in all the dust and the gas and the compact remains of stars, you don't have enough matter. And this is one of the primary evidence for dark matter, that beyond the center of the galaxy, there's this vast halo of transparent matter that has mass and gravity, but doesn't interact with light in any way. And it is vast. If we shrink down and say this is the visible portion of our galaxy, there is at least 10 times as much dark matter as there is invisible matter in all the stars and gas and clouds combined. And this is an invisible component of our galaxy, but it is the key component of our galaxy. It's the one we know least about, but it's the one whose gravity keeps the whole galaxy together. And it's one of the most exciting areas of astrophysics. And especially as it's an area where it intersects perhaps with particle physics. And so there's this whole growing field between particle physicists and astronomers to understand the nature of dark matter. We can also weigh the galaxies. You might say, oh, there's something strange about the stars. But there are little galaxies in orbit around our own galaxy. If you're lucky enough to see the galaxy from the southern hemisphere, there are two little galaxies in orbit around it. These are known as the Magellanic Clouds. And these are all distorted and pulled out of shape. And there's lots of star formation because the gas clouds from those little galaxies, and they're each about 100th the mass of our galaxy, and they're just beyond the disk. So maybe they're about 160,000, 200,000 light years away from us. But they're getting squashed and stretched by the gravity of our galaxy, and they're in orbit around it. And they're creating stars, but they're also getting shredded. If we look at a visible image of our galaxy and then move to a radio picture, which shows you gas, they're being torn apart, and they're leaving this trail of gas in their wake. And so our galaxy is gradually destroying these little dwarf galaxies around it. But we can use the speed and the distance at which they rotate our galaxy again to, confirm the idea of the amount of dark matter out there. So this is just a schematic showing how these dwarf galaxies get shredded, and they perhaps only last 2 billion years. And those aren't the only 2 dwarf galaxies around our galaxy. We form part of what's known as the local group. You have our Milky Way galaxy, and it's got surrounding perhaps 10, 20 dwarf galaxies out beyond it. And then our local group has got 3 large spiral galaxies, each with their smattering of dwarf galaxies around them. And our nearest neighbor is the Andromeda galaxy. It's the only galaxy beyond the Magellanic Clouds that you can see with your unaided eye, and certainly the only one you can see in the Northern Hemisphere. And it's very similar to our galaxy. You can see it has 2 small dwarf galaxies in orbit around it. But even at 2.5 million light years away, it is close enough that our galaxy feels its gravity and it feels our gravity. And we are moving together at about 1 million kilometers per hour. So imagine this is about to scale. You have our Milky Way in the top left. You have the Andromeda galaxy in the lower right, moving together at 1 million kilometers an hour. So that means they're going to crash into each other. We reckon this will happen in about 6 billion years' time. And we want to know what happens. And of course, we're impatient. So we do modeling, numerical modeling. And here's just a very simple schematic. Obviously, it's sped up because we don't have 4 billion years, whatever, to watch this little movie. So the ticker tape's in the lower left-hand corner. Now, this is our galaxy. It's rotating, as I told you, every 240 million years. And as we zoom out, you see the edge-on view of our galaxy. And in the lower right-hand corner of the movie, you will see Andromeda coming in. Now, when 2 galaxies smash together, it's not the case, it's not like a car accident where 2 cars lock together or what have you. Instead, it's a much more sort of fluid thing. And so they'll kind of sploosh through each other and past each other. But look what happens. Tails of stars get drawn out. Again, this is through the gravitational tidal forces. They pull out long streamers of stars from each galaxy. And they go so far, but gravity will pull them back together. And they'll go through various splooshes through. And gradually, perhaps in about 6 billion years' time, they will form a new system. And our Milky Way would no longer look like the nice fat spiral we see here, but it and Andromeda will have fused together to form a new galaxy. Now, of course, we don't know what that's going to look like. I will say in 4 billion years' time, that's about the same time as we expect our sun to explode in a nova and form planetary nebulas. So who knows what's going to happen to the Earth? Who knows whether the sun's going to be one of those tails of stars drawn out of the galaxy? But imagine we could just watch this from the surface of the Earth. We will gradually see Andromeda come closer, and gravitational forces will squeeze and stretch those gas clouds, cause masses of star formation, those pink nebula, blue star clusters, which will then gradually form and fade and form a new site in our sky. And so this is what we think our galaxy will look like in about 7 billion years. So if I were giving this talk in 7 billion years' time, well, you can reckon I'd be giving a very different introduction to our galaxy. So thank you very much.
Thank you, Carolyn. That was incredibly inspiring. I think we'll all be encouraged to be looking up a bit more, which is good for us at the moment, I think. So a lot of questions, so we'll do our best to get through the questions. First question, actually 2 questions from Alex. What happens when you get sucked into a black hole, and can stars freeze?
Oh, okay. Just taking the second one, can stars freeze? No, I don't think so. The main fundamental quality of a star is that it is hot because it is providing energy at the center. So the surface of our sun is like 6,000 degrees. The core of our sun is like 12 million degrees. So if you have a star that is frozen, that is so cold, it's no longer going to be a star. A star, by definition, is producing that energy to its core. So I can't think of how you get a star to freeze. You might get a star that goes cold, if it's not very massive, so it doesn't become a white dwarf or a neutron star or a black hole, it just runs out of energy. It may sit there and it may get very cold, but it'll take billions of years to do that. Second question, what happens if you get sucked into a black hole? Well, we don't know. I will stress this is not an experiment we've done. But if you study the mathematics, the thing is, it's not just gravity is strong close to a black hole, but there's gravity, the amount of gravity changes very quickly in the vicinity of a black hole. So imagine you do the unfortunate experiment of stepping over what we call the event horizon. So that's the point of no return around a black hole. If that defines, if you like, the size of a black hole. Imagine I step over that, or maybe I'm falling towards a black hole and say I'm going feet first. Well, my feet feel a stronger gravity than my head does. So my feet get pulled towards the black hole faster than my head, so I get stretched. And then the difference between my feet and my head gets even stronger, and I get stretched some more. And so this applies not just to if you throw a person, some poor astronaut at a black hole, it applies to planets and stars and gas clouds. They go through a process which we think is called, well, we call it spaghettification. The things get stretched and elongated and virtually shredded. So it's this tidal gravitational force that just pulls things apart and shreds them. And beyond that, what happens when you cross over that event horizon? Well, we have no idea. You can read lots of speculation in books, but one of the fascinating things about astronomy is there are places where we currently don't have the physics to understand them. And there are 2 prime cases. One is what happens within a black hole, and one is what happens in the very early universe in the Big Bang. And this is where our current understanding of physics doesn't quite work. We can't combine gravity, what we understand about gravity, with what we understand about particle physics and what happens on tiny scales. So again, fascinating area to study.
Great, thank you. Leading on from that, what is your advice for someone who is 10 years old and wants to be a professor of astrophysics?
One of the great things about astronomy is there's lots of it available, both on the television. I'm thinking of some of the BBC documentaries. There are some fabulous books out. The other thing is, if you can go out and perhaps look at the night sky. That's how I got into astronomy, because I just thought it was beautiful. I got interested in stars. I got interested in watching for satellites coming over. I got... you don't have to have a telescope. If you've got a pair of ordinary bird watching binoculars you can borrow or somewhere in the house, next time you can see the moon, have a look at the craters, have a look at the structures on the moon. It's very underrated, and yet it's fascinating to look at. If you are lucky enough to live somewhere perhaps near a city, but it depends where you live, there are astronomy clubs. They're very keen amateur astronomical clubs. Sometimes they run kids clubs. Sometimes they're very welcoming to younger people to come along. You may not understand everything that goes on in a talk, but some of the talks may be interesting. You'll learn more about astronomy. Maybe there'll be people there who have telescopes that they'll go and let you look through. So ask around, see what's available. But my best thing to recommend is stay interested in astronomy. Even if you can't join the astronomy club, see what's online. If you're into books, look in your library, see what books there are. look at Hubble Space Telescope pictures. Just keep that interest up and find out, keep reading, find out as much as you can. And the more curious you are and the more questions you have, the more likely you are to be a proper scientist and more likely to become that professional astronomer. So good luck.
Yeah, wonderful. Another question from somebody wondering, because they're inspired by these beautiful pictures, whether you ever wanted to be an astronaut.
Oh, did I ever want to be an astronaut? To tell the truth, I'm too much of a coward. I was discouraged at an early age from any idea of being an astronaut because I have very bad eyesight, and certainly at the time they wouldn't recruit people with, you know, my kind of eyesight. But I am less interested in being out in space myself. I don't feel I need to be out in space. I tend to think of my spaceship as planet Earth. And I wouldn't see the universe any differently from being out in space than I do really here on Earth. So if you like, I am quite content to sit on the Earth. You know, I use data from telescopes out in space. I use, you know, even telescopes on the International Space Station. So I use instruments that are actually in orbit around the Earth. But myself, I'm quite content to leave the adventuring, being out in space, to much braver people. And also, you know, people who can maybe do other kinds of science, because one exciting things about being astronauts is it's not just astronomy that you can do from space. There's engineering, there's biological studies, there's physiological studies about how space and space travel affects the human body. So we need a whole range of different types of scientists out there in space, and I think astronomers come pretty low in the pecking order.
I'm with you. I'm not brave enough to go on a space flight. Gregory would like to know if time flows differently on different planets.
Oh, got shades of Interstellar coming here, I think.
Yes.
The key thing here is time flows differently in different gravitational fields. So if you have time passing on the Earth and time passing on a much more massive planet, then there is going to be a difference of perception. You don't notice it yourself, but it's the comparison between the two. So, for example, even on Earth, there is a difference in time between the surface of the Earth and, say, jet planes flying around the Earth. Or even in an extreme, not that you can measure it, but just from the bottom of a tower block to the top of a tower block. So what is important is the amount of gravitational force that you experience, and that's how, and the stronger the gravitational force, the slower the time.
Wonderful. All right. I think we have time for two more questions, but probably shortish answers. The first is somebody wanting to know if there's any point getting their own telescope. So you talked about that a little bit, or should they just look at pictures from better telescopes? And then another question is, do you have a favorite star and why?
Okay, so the first question about telescopes, if you just want to look at planets and what have you, and some star clusters and things and the moon, I will stress binoculars are very good. A small cheap telescope is probably not worth getting. Again, if you were lucky enough to have an astronomy club near you, you might be able to borrow a telescope. So you can experiment and, you know, borrow it for a couple of months and see what kind of telescope you like. And if you can do that, I'd recommend that. But personally, I think there's a lot to be said for actually looking at the sky yourself, but I'm biased. That's how I got into astronomy. So yes, borrow a telescope, but don't necessarily buy an expensive one until you found out a bit more about them. And the second one, do I have a favorite star? Well, do you know, I don't. I love them all. I just love the fact they're out there. I love looking at them, and whichever is my favorite will vary from, you know, one time of year to the other, because you see different stars in the summer than you see in the winter. But I'm quite partial to Betelgeuse, which you may know is the left armpit of Orion. Nice red star, easy to identify. everybody knows it. And when I'm telling people how to find their way around the night sky, it's a great starting point. So if I had to choose one, it would probably be Betelgeuse, but I can only see it in winter.
Yeah, and very cool name.
Yeah, very cool name.
So I'm afraid we have to leave it there. There are more questions, but Carolyn has kindly offered to answer those. We will, I think you need to probably email those questions. So do we have an email address that we can share with everybody? We'll try and display that shortly. But I'd like to take the chance to just thank you, Carolyn, for such a wonderful talk on a Sunday morning. And I think you've inspired future generations of astronomers. So we will try and display Carolyn's email address, or try and get in touch with you to let her know what that is. I don't want to publicly announce it here. So thank you again to Carolyn. Thank you to all of you for listening, and enjoy the rest of your Sunday. Remember to look up.